Good evening, students. Welcome to today's physics session. Welcome to 12th physics class. Okay. So today topic is electric charges and fields. Clear? Okay, good. So before we launch our interactive virtual laboratory on screen, let me take you back to June 1752 in Philadelphia. I will share the one image. Okay. Yes. So imagine a stormy afternoon with the dark clouds hanging low and thunder cracking through the sky. A man named Benjamin Franklin walks out into the open field holding a silk kite attached to a hemp string. You can see that, yeah, in the image. A silk kite attached to a hemp string with a metal key dangling near his hand. People at the time thought lightning was a divine, mysterious force completely separate from anything on earth. Okay. Franklin flew his kite right into the thunderstorm cloud as the rain wetted the string, making it conductive. Making it conductive. Loose threads on the kite string suddenly shoot up and repelled each other. Okay, as the rain wetted the string, making it conductive, loose threads on the kite string suddenly shoot up and repelled each other. When Franklin brought his knuckle close to the metal key, a bright spark jumped. A bright spark jumped, shocking his hand. So, in that single moment, Franklin proved a revolutionary idea. The giant spark in the sky, that is lightning. Okay, and the tiny crackling spark you feel when you pull off a woolen sweater in a winter are the exact same physical phenomena. The physics began that static electricity. The giant spark in the sky, that is lightning, and the tiny crackling spark you feel when you pull off a woolen sweater in winter are the exact same physical phenomena, static electricity. Clear? So Franklin realized that matter does not create electricity out of nowhere. Okay, matter does not create electricity out of nowhere. Rather, objects contain electric charges. Okay, so object contain electric charges that can be transferred from one body to another. So today we know this transfer happens at the subatomic level through the electrons. Okay, so electron already you are very know about that electron, yeah, and as well as electric charge. So electric charge is a fundamental scalar property of matter. Is it correct? Fundamental scalar property of matter. It obeys three core laws. It obeys three core laws. What is that? First one, conservation. Charge can neither be created nor be destroyed, only be transferred. Okay, only we can transfer. We cannot create the charges or destroy the charges. Is it clear? Okay, good. Then next property, additive. The net charge on a body is a simple algebraic sum of all individual charges. So, for example, in your class, there is a term average mark of that section, 12th A or 12th B. So that means, so algebraic sum of all the students' mark divided by the total number of students in that section. Yeah, is it so? So same like that additive property for the electric charge. Net charge on the body is a simple algebraic sum of all individual charges. And the third one, very important, quantization. Any observable charge Q in nature is always an integral multiple of basic fundamental unit E. You can see in that image. Q is equal to plus or minus NE. Yeah, plus or minus NE. So N means any value from 0, 1, 2, 3, like that. Okay. And E, fundamental unit of charge, that is fundamental unit E, 1.602 into 10 power minus 19 Coulomb. Okay. So, key takeaway: curiosity, observation, and courage, which is equal to discovery. One spark of curiosity can light up the world. So, from rubbing amber to studying lightning, the principle is the same. Nature is consistent. Three different observation, one common effect: amber plus wool. Amber, when rubbed with the wool, attracts small pieces of paper. Silk plus glass rod. Silk rubbed with the glass rod can lift light objects. And lightning from clouds creates a powerful electrical effects. Same effect, same cause, static electricity. Clear? Okay. And core concept, static electrification. When two materials are rubbed together or brought in contact and then separated, electrons move from one body to another. Okay, underline that word. When two materials are rubbed together or brought in contact and then separated, electrons move from one body to another. So before, natural bodies and the transfer of electrons move from one body to another. After, one body loses electron, so which becomes as plus, positive. The other gains electron, which becomes as negative. Clear? Okay. So now let's test our fundamental concepts before we launch our interactive virtual laboratory. I will share the 3 MCQ session. Okay. So I will here you can see that. Okay. So before that, okay, once again, I will again share the screen. Okay. Now it's clear. So which subatomic particle is transferred between solids during frictional charging? You can type the answer in the chat box. Which subatomic particle is transferred between solids during frictional charging? Yes, good. Electron. Option C. Yes, correct answer is electron. Good. So the protons and neutrons are tightly bound inside the atomic nucleus by the strong nuclear force. Electron, especially outer valence electrons, are loosely bound and can easily transfer from one atom to another when friction is applied. Yeah. So that's why answer is electron for this question number 1. Now question number 2. Two perpendicular forces of equal magnet F act at 90 degree. What is the resultant magnet? What is the resultant magnet or resultant force? 2F, root 2F, F by 2 or 0. It's answer. Okay, good. That is answer is B, root 2F. By applying a Pythagorean theorem for vector addition at right angles, F net root of F square plus F square plus 2F cos 90 degree, you will get the root of 2F square. So then we will get the root 2 into F. Is it clear? Okay, good. So answer is option B. Clear? Okay. So keep this vector addition rule in mind, as we will use it shortly when studying the superposition principle of electric forces. Clear? Now question number 3. According to Newton's third law, if charge 1 exerts a plus 10 Newton force on charge 2, what force does charge 2 exert on charge 1? According to Newton's third law of motion, if charge Q1 exerts a force, electrostatic force, okay, plus 10 Newton on charge 2, what force does charge Q2 exert on charge Q1? Plus 10 Newton in same direction, minus 10 Newton in opposite direction, plus 20 Newton in same direction, 0. Yes, according to the Newton third law, every reaction has an equal and opposite reaction. Okay, so plus 10 Newton force acting at that object, that charge will exert a minus 10 Newton in the opposite direction. So option is B. Is it correct? Option is B. Electrostatic forces form an action reaction pair. So F12 minus F21. Is it so? Clear? You can see that answer. All the answer. Good. So the forces are always equal in magnitude and the opposite in direction along the line joining the two charges. Okay. Now let us switch our main display directly to our interactive physics simulation laboratory. I will share the screen again to show the simulation. Yes, here you can see the simulation. Okay. So on your screen, you can see that the electroscope induction, Coulomb's law and vectors, electric field lines, particle trajectory, electric dipole. And here you can see that gold leaf electroscope interactive lab. Look at the main screen. Look at the main screen. We have a virtual gold leaf electroscope. Virtual gold leaf electroscope. It consists of a vertical rod connecting to the conducting knob at the top and the two gold leaves at the bottom, housed inside a grounded glass jar. Is it clear? Step number 1. So we have to charge a rod. So charging by friction. When I click the rub rod, that is plus 5 microcoulomb button, we rub a glass rod with a silk. Okay, we rub a glass rod with a silk. So electrons transfer from the glass to silk. Yeah, electron transfer from the glass to the silk, leaving the glass rod positively charged with plus 5 microcoulomb. You can see that. You can see that. Okay. So rod charge quantity, you can see that plus 5 microcoulomb here in the left hand side. Left hand side. Yeah. Okay. Right. So charge accumulate the charge rod accumulate the charge plus 5 microcoulomb. Now watch the simulation canvas as I drag this positively charged glass rod close to the metal knob like that and like that. Okay. So glass rod close to the metal knob without touching it. Observe what happens. That is, negative electrons inside the metal rod are attracted upward to the positively charged glass rod. Okay, negatively charged inside the metal rod are attracted upward to the positively charged glass rod accumulating on the metal knob. The live metric shows a induced charge on the knob minus 2.7 microcoulomb. Okay, here the knob induced charges minus 2.7 microcoulomb. Okay, so this leaves a deficit of electrons at the bottom, giving the gold leaves a positive charge. You can see that plus symbol. Negative electron inside the metal rod are attracted upward toward the positive charged glass rod accumulating on the metal knob. The live metric shows the values, and this leaves a deficit of electron at the bottom, giving the gold leaves positive charge like that. Here you can see that leaf net charge plus 2.7 microcoulomb. Same charges of what knob induced charge, but that is minus. This is plus. Same charges. Okay. Because both the gold leaves carry like positive charge, they push upwards. Correct? Look at the divergent angle. Theta is equal to 20 degree. Okay. Now, step number 3. Conduction with grounding. If I click the touch knob, you can see that if I click the touch knob, which means the glass rod touch the metal knob. Okay, clear? So the physical contact allows free charge transfer by conduction, permanently charging the leaves. Clear? Okay. Now, if I click the ground, earth, you can see that yes, electron flow from the earth into the leaves to neutralize the excess positive charge. If I click the ground, earth button, electrons flow from the earth into the leaves to neutralize the excess positive charge, causing the gold leaves to collapse back to the like 15.0. Okay. Clear? Okay, right. So key takeaway from this step: induction redistributes internal charges without direct contact, where conduction transfer net charge permanently through the physical contact. Okay. Now we can go into the tab number 2, Coulomb's law and the vectors. Let us transition to our important concept to study the Coulomb's law quantitatively. On screen, we have a 2-point charges, Q1, Q2. Q1, here you can see that value plus 5 microcoulomb, and Q2 charges minus 5 microcoulomb. So unlike charges. So this is in red color, this is in blue color to show that different charges separated by the distance. Oh, for example, we can put the distance like that. You can see that. Yeah, 1 meter. For example, we can take this as a reference. So separated by the distance r is equal to 1 meter. Step number 1, inverse square distance scaling demonstration. That is, Coulomb's law said that magnitude of the electrostatic force between the two stationary point charges is given by, already you know that the formula F is equal to K into Q1 by Q2 by R square, or otherwise F is equal to 1 by 4 by epsilon naught into Q1 Q2 by R square. Is it correct? Where K is the 1 by 4 by epsilon naught, which is equal to 9 into 10 power 9 Newton meter square by Coulomb square. Now, at R is equal to 1, R is equal to 1, you can see that 1 meter the whole square. Charges Q1, Q2 plus 5 microcoulomb minus 5 microcoulomb. And K, already you know that value, 9 into 10 power 9. So F is equal to 0.23 Newton between these two charges in this distance. So force, this is the force of attraction because these two are unlike charges. So 0.23 Newton. Now pay close attention. I will click the R by 2 half, R by 2 half. Press preset button to reduce separation to R is equal to 0.50 meter. I reduce the distance between the two charges into half. So previously I am putting 1 meter, now 0.50 meter. Now look at the green color value, 0.90 Newton. Yeah. So they instantly expand. The live calculated force leaves from 0.23 Newton from previous case to 0.90 Newton. So halving the distance multiplies the force by 4 times. Okay, if you reduce the distance by half times, the force will be 4 times. This visually proves that inverse square law. F is directly proportional to 1 by R square. Okay, F is directly proportional to 1 by R square. Is it clear? Okay. Now I will click the third charges, and already you know that for like charges you can calculate the same values with the respective distance, but it does not depend on the charges, that is plus charges minus charges, because in our formula we have to put the modulus. So that means if you take the minus q charge or minus 5 charge, so we have to take only values, only we have to take 5 only. So forces are there, 0.90 Newton. And now I will click the third charge. superposition button. A third charge Q3 is there, appear there. Yeah. Okay. For unlike charges, like that, you can see that. So Q3 here, you can see that purple color appears, plus 3 microcoulomb. Notice how charge Q1 now has two distinct force vectors acting on it. Yes. So charge Q1 has two distinct force vectors acting on it. Vector F12, vector F12, vector F12, which is shown by the green line, pulling Q1 toward Q2. Vector F1 to F13, vector F113, purple, repelling Q1 away from Q3 because Q1, Q3 same charges. Q1, Q2 unlike charges. So green pulling, purple repelling Q1 away from the Q3. So the gold arrow represents the net resultant force vector F net. According to the principle of superposition, the total electrostatic force on any charge is the vector sum of the individual forces except by the all other charges. Okay, so that's why I am putting F net, 1, which is equal to F12 plus F13. F12 plus F13. F12 means the force between the charges 1 and 2, 0.90 Newton, and F13, the force between the charges 1 and 3, 0.30 Newton. So net force means we have to add those values. So which gives the 1.40 Newton. Clear? Okay. So superposition principle, the net force acting on the charge Q1 is the vector sum of the individual forces exerted by the Q2 and Q3. Okay, net force acting on the charge Q1 is the vector sum of individual forces. The electrostatic forces obey the inverse square law with the distance and combine vectorically using the parallelogram law of vector addition. Now we can move into the third tab, electric field lines. So here you can see that, let us visualize the invisible electrical environment using electric field lines. First introduced by Michael Faraday. Field line. Observe the dipole on the screen, plus Q minus Q. Exactly 12 field lines originate from the positive charge and terminate symmetrically on the negative charge. Look at the bright arrowheads, the direction of an electric field line. At any point indicates the direction of the net electric field vector E. Okay, the bright arrowheads denotes the direction of electric field line at any point indicates the direction of net electric field vector E. Where field lines are crowded close together near the charges, the magnitude E is strong. Where they spread out, the field is weak. Okay, and the field lines never intersect each other, because if they did, the electric field at the intersection point would have two different directions simultaneously, which is physically impossible. Already you know that. Yeah, if the field lines intersects, the electric field at the intersection point would have two different directions simultaneously. How is it possible? Which is physically impossible. So field lines never intersect each other. Clear? Okay. So now I will go into the uniform plates. Here we have two parallel charged plates creating a uniform upward electric field E 2.0 into 10 power 4 Newton per Coulomb. Here you can see that value, electric field created by the two parallel plates. When a charged particle of mass m and charge q is dropped into the uniform field, it experiences an electrostatic force. You can see that. Okay, electrostatic force. When a charged particle of mass m and charge q is dropped in the uniform field, it experiences an electrostatic force F is equal to q into E, producing an acceleration. A is equal to QE by m or EE by m. We can put the small e or small q in that charge. Okay. So now click the drop electron. Yes. Watch the blue dot accelerate rapidly downward to the positive plates. The measured fall time for the distance h is equal to 1.5 centimeter. So time is equal to root of 2h me by E. So which gives 2.92 meter per second. Now click the drop proton. Click the drop proton. Watch the red dot much slower to the negative plates. Its measured fall time T of P is root of 2h mp by E. Yeah, 125.4 nanosecond. Clear? Why does the proton take over 40 times longer to fall the same distance? Think about that. For electron, it takes only 1.5 centimeter distance and time 2.92 nanosecond. For the same height, the proton take over 40 times. That means 125.4 nanoseconds. Because proton's mass mp equal to which is approximately 1.67 into 10 power minus 27 kg, which is 1836 times heavier than the electron mass. Already you know that mass of an electron me approximately 9.11 into 10 power minus 31 kg. For the proton it is minus 10 power 27 only, but for the electron minus 10 power minus 31. So higher mass result in the smaller acceleration for the same magnitude of the electrostatic force. Clear? Okay. Now electric dipole. So click on the tab 4 electric dipole. Let us navigate the electric dipole. A pair of equal and opposite path charges plus q minus q separated by the distance 2a. First of all, we have to find the dipole moment vector. Look at the green vector P connecting minus q and plus q. The electric dipole moment is defined as the, already you know that formula, P is equal to q dot 2a. P is equal to q dot 2a. It is a vector quantity pointing strictly from the negative charge toward the positive charge. Okay, it is a vector quantity pointing strictly from the negative charge toward the positive charge. And torque. When an electric dipole is placed in a uniform electric field E at an orientation angle theta, the charge plus Q experiences a force plus Q plus QE along the field, and the charge minus QE minus Q experiences equal and opposite forces minus QE against the field. When the electric field is placed on the uniform electric field E at an angle, at an orientation angle theta, charge Q experiences a force plus QE, and the charge minus Q experiences equal and opposite forces against the field. And the net translational force is F net is equal to 0. However, because these two equal and opposite forces act along the different lines of action, they form a couple that exert a net restoring torque. That is, dou is equal to P cross E, which is equal to PE sin theta. Okay. So at orientation theta is equal to 0 degree, like that is parallel alignment, sin theta, sin 0, 0, dou is equal to 0. Okay, the dipole is in the stable equilibrium. At theta is equal to 90 degree, like that, 90 degree perpendicular. Sine 90, 1. Tau is maximum. Tau gives P. Torque reaches its absolute maximum. When theta is equal to something other than 180, like that. Antiparallel. Sine 180, 0. Tau also 0. However, any tiny disturbance will cause it snap around. This is unstable equilibrium. Okay. Now I will set the value theta is equal to 30 degree and click the release and oscillate button. You can see that the restoring torque continuously pulls the dipole back toward theta is equal to 0 degree. Here you can see that. Yeah. Clear? Angle is 0 degree. So the restoring torque continuously pulls the dipole back toward theta is equal to 0 degree, causing it to undergo simple harmonic angular oscillation about its stable equilibrium position. Clear that? Okay. Okay, students. Now it is a time for numerical problem. I will stop the screen and I will show the numerical problem screen. Let's discuss the numerical problem with two important concepts which were discussed today. Okay. Now you can see that screen. Yes. Okay. So first problem, Coulomb's law and distance scaling. 2-point charges. Q1 plus 2 microcoulomb and Q2 minus 4 microcoulomb are separated by the R is equal to 0.3 meter in air. Clear? Okay. So here we have to find the Coulomb force. Yeah. So the 2-point charges Q1 and Q2 are separated by the distance. Take a look at the diagram on the screen. We have a positive red charge and a negative blue charge. What do you know about opposite charges? What do you know about opposite charges? Yes, they attract. Exactly. Yeah, they attract. Notice the green force arrow are pointing toward each other. Okay. First of all, in part A, we need to find the exact magnitude of the force. Okay. So the law we use to find the force between the 2-point charges is Coulomb's law. Is it correct? The law which we use to find the force between 2-point charges, Coulomb's law. Right? Correct. Very good. So our formula K is equal to F is equal to K into Q1 Q2 by R square. Remember, we use the absolute values of the charges here because we just want the magnitude of the force. The sign just tell us the direction. Let's plug our numbers into it. K is equal to 9.0 into 10 power 9 Newton meter square by Coulomb square. Now put that values. Q1, Q2 and the distance. R 0.3 meter. So 0.3 the whole square. Clear? Next step. Simplify the numerator and denominator. We will get the F is equal to 72 into 10 power minus 3 by 0.09, which is equal to 0.072 by 0.09. Okay. Right. So let's put our electrostatic constant K value 9 into 10 power 9 also. Our charges in the microcoulomb. So we must write them into 10 power minus 6. Okay. Our distance is 0.3 meters. Numerator simplified to 0.0072 and the 0.3 square to 0.09. Let's see the final results. 0.8 Newton attractive. Clear? The force is attractive because the charges have opposite signs. Clear? Okay. So the initial attractive force is 0.8 newtons. Now here is where it gets interesting. What if we move them closer together? Part B says we have the distance to 0.15 meters. For example, part B, new distance, R dash equal to 0.15 meter. Part B says we have the distance to 0.15 meters. Instead of recalculating them from scratch, use the inverse square relationship. Okay? Because Coulomb law has R square in the denominator. It follows a inverse square relationship. We can just multiply our old force by the ratio of distance squared. Now, click the next step. F is equal to 0.8 Newton. Already we got. And the ratio of distances. New distances and previous distance. 0.3 by 0.15 the whole square. Which gives the 2 the whole square. 2 square means 4. So 0.8 into 4. 3.2 Newton. 3.2 into Newton. Since we have the distance, the ratio of R to R dash is 2. So we just multiply our original force by 2 square, which is 4. As the note says, this is a classic exam trick. If you have the distance, you don't just double the force. You multiply it by 4. If you cut the distance in third, the force increases by 9. Always look out for that inverse square relationship. Now, let's move from two isolated charges to special setup called electric dipole. Here, electric dipole. Let's put it inside the exiting electric dipole. Okay. An electric dipole with the charges Q is equal to plus or minus 5 microcoulomb separated by the distance 2a equal to 4 centimeter, that is 0.04 meter, is placed at theta is equal to 30 degree in a uniform field. E is equal to 2.0 into 10 power 5 Newton per coulomb. Look at our diagram. The blue lines pointing the right present a uniform electric field. Inside it, we have our dipole tilted at a 30 degree angle. First things first, we need to calculate the dipole moment defined by the letter small p. The formula is simple. Yeah. P is equal to Q into 2a. But be very careful here. A common mistake is to plug in half the distance for 2a. The variable 2a represents the entire distance between the charges. Okay. The variable 2a represents the entire distance between the charges, not the half distance. Okay. Now, click the next step. The formula for dipole moment 2a p and substitute the given values. We take the magnitude of the one of our charges 5 into 10 power minus 6 coulombs and multiply it by the total separation distance, which we convert into 0.04 meters. Okay. Now next step. That gives us a dipole moment 2.0 into 10 power minus 7 coulomb meter. Now for part B, the electric field is going to push on the positive charge and pull on the negative charge because they are at an angle theta. This creates a turning force. What is the physics term for turning force? The electric field is going to push on the positive charge and pull on the negative charge, because they are at an angle theta, it creates a turning force. What is the physics term for the turning force? Yes, correct. Torque. Very good. Torque. So let's find out how much torque is twisting this dipole. Next step. Torque. So already we know that formula tau is equal to P sin theta. The magnitude of the torque on a dipole is tau is equal to P sin theta. Let's plug in what we know. P, dipole moment, already we got 2.0 into 10 power minus 7, and E, electric field in our formula, and sin 30, that is angle 30 degree. And next step, sin that is 0.5, we can put that, and 2.0 into 2.0, 10 power minus 7, 10 power 5, which gives 0.04 into 10 power into 0.05, 0.5. Now we will get that tau is equal to 0.02 Newton meter. Is it clear? Okay. Okay. So this gives a final torque of 0.02 Newton meters. So before we move on, look back at the diagram. You can see that green force arrow pointing in opposite direction. The positive charge wants to move with the field. The positive charge wants to move with the field, and the negative charge wants to move against it. So this torque will always try to twist the dipole, and it perfectly lines up flat against those blue field lines. Okay. This torque will always try to twist the dipole until it perfectly lines up flat against those blue field lines. Once it aligns, the angle is 0. The sign of 0 is 0, and the torque becomes 0. Torque becomes 0. Clear? So already I showed that in our class by using simulation. Now this is a numerical problem. Okay. So that's all for today. If you have any doubt, chat in the box. You can type the answer or doubts in the chat box. Okay, no doubt. Okay. Thank you. Jai Bharat, Jai Hind, Jai Vityas. Thank you.